And I will assume that the first isobar line is that 140. Say that the P1 is 140 kilopascal, and the P low, let's say P medium, it is at 280, and the P that maximum or P high is that 720 kilopascal. Okay. So let's draw it. So firstly, you will have the refrigerant that goes from 1 to 2, and the 1 is the minimum, and the 2 is same as 3, and it is maximum. You just add the P3 is same as P2. This is the maximum. So for the first compressor, I will travel from 1, this is 0.1, to 0.2, which is the maximum one. This one should be the isentropic line here. This is 2. Okay. And from then 2 to 3, you will have the condenser. Pressure drops, so the pressure is constant. You will have 3 here. And then you have the thermal expansion valve, first one. Okay. And for the first thermal expansion valve, you will have the evaporator. For that evaporator, you are doing some amount of the cooling here, and you end at cooling, which is at 5. This is 4, and this is 5. You can see the temperature here, it is 0 degrees Celsius. And you are using second thermal expansion valve here, and you drop the temperature one more time. You can see it is dropping into negative 20 degrees Celsius. Okay, and this one will be at 6 here, and then back to 1. Okay. So you are doing additional cooling effect here. You can see you have 2 coolings, and that first cooling is that QL1. It is 4 to 5, and the QL2 is that it is 6 to 1. And this one happens at 0 degrees Celsius. This one happens at negative 20 degrees Celsius. This one is refrigerator, and this one is that freezer. Okay. Good. And the one more refrigeration cycle is that intercooled cycle here. For the intercooled cycle, so we are using the intercooling between 2 refrigerants, between 2 compressors. Okay, now let's see that one. If you remember, this one was very similar to Brayton cycle here. You have the compressor one here, and then outlet of this one is there is some inlet which is 1, and outlet is sent to intercooler here, and it is sent back to second compressor 2. So you have this outlet as 2, and then you have that 3. This component here, it is intercooler. So you are cooling it. Say that you have some external agent here. This external agent cools that system. Okay, then you will have the compressor 2. The next components will be the same here. You will have this as the condenser, and then you will have the TXV here, and then you will have the evaporator, and then you will have this process back to the initial state. Okay. So, but here you will have that, just say that you have this P1 is the same. Let me just put some numbers here. So 1, 3, 4, you have that 5, 6, and then you have the same as 1. P1 is same as P6, okay, and the P5 is same as P4, and the P4 is greater than P3, and the P3 is same as P2, and the P2 is greater than P1. Okay. This P2 or P3 value, they are the same. It is intermediate pressure. Okay, what I will tell is that P1 is that 140 kilopascal. Just write it. P2 is similarly 280 kilopascal, and the P3 is 720 kilopascal. Let's just do it. Let's go from 1 to 280 here. Okay. Then I will have the intercooling here. The intercooling effect means that from 2 to 3 intercooling, and the entropy S drops. So you have the T drops. Temperature and entropy drops. You will go in that direction here. say that it will be 0.2, and it is 0.1, it is 0.3 here, and then I will move the second compressor, which goes from 3 to 4. This one is 4, and then from back to 5 here, just go back to here, it will be 5, and then from 5 to 6, we'll have the thermal expansion valve here. This thermal expansion valve drops the pressure to the initial value. Okay. And back to 1. Okay. So what is the advantage here? The advantage is that if you have done the compression process from 1 to 4 without using an intercooling effect, so say that if you have done the process in this manner, okay, this one will be at 4 prime. So this one is without intercooling. You can see that now the H4 prime has the 4 prime has more enthalpy than the 4. H4 prime is more than H4. If it has more enthalpy than the 4, it means that the work in 4 prime and between 1 and the 4 prime is greater than the work in between 1 and the 4. You can see the effect here. So you will have that more work that is required to compress the refrigerant here. Therefore, you have decreased the amount of the work by using an intercooler here. It's intercooled cycle. And next comes the cascade refrigeration cycle here. And here we are using the same refrigerant. And let's see how it happens in the cascade refrigeration system. So we draw the components here. So I have the compressor 1. Then from that compressor, I have the same condenser 1 here. And that back to thermal expansion valve. And then I have the evaporator. I'll just put that one here. That means that it is evaporator. We just put numbers here. So it will be that 1, this one 2, this one is 3, this one is 4, and back to 1. Okay, so let me just put the 4 sign in a different place because I will need a space here. 4. Now I am adding the next refrigeration cycle here, but this one will be the lower part. And for that refrigeration cycle, so I have the compressor. So these are cascade. So this one is that topping cycle. Now I will have the bottoming cycle here. So that there is compressor 2. This one has some outlet here. So there is some inlet for that compressor. This one is say that 5. Then you have the 6 here. Then it goes in that direction. You will have the same process and it goes to, so for the topping cycle, this one is evaporator. Just write the name of it. Okay. But for the bottoming cycle, this is the condenser. Condenser. Okay. And then you have gone back to the thermal expansion valve here, TXV2 here. This one is the TXV1, TXV2 here, and then back to evaporator. Okay, and then back to compressor. This is 5, 6, 7, and 8. You can see that this one is the topping cycle and this one is the bottoming cycle. So you are using the same cycle, but the main thing here is that you have one heat exchanger there. Okay, heat exchanger, and the Q out of condenser will be the same as Q in of evaporator. We are using the heat transfer from the condenser. If I just write it here, so that condenser will give us the heat in that direction, and this one will use the evaporator will use that heat here. Okay, this is the heat exchanger. Now if I draw the topping cycle and the bottoming cycle on the TS diagram here, you will see the advantage of this one. And this topping cycle has higher pressure than that one, and as you can notice now, so that here you have two isobar lines. Okay, and here you have also two isobar lines. Okay, now let's say that this one has the isobar lines. Let me just write it. P1 is same as P4, P2 is same as P3 here, and the P5 is same as P8, and the P6 is same as P7. Okay, so that P2 is the maximum pressure. Let's take as this one as 720 kilopascal, and the P1 and the P4 is at 280 kilopascal here. And the PC5 and the P8 is the minimum pressure. I will take it as 140 kilopascal. Okay. P6 and the P7, I will take the same pressure here, but you can take any pressure, any. It can be different because this one there is no mixing. 180 kilopascal, but you can take any pressure since no mixing. Okay. Here you don't have any mixing. Okay, this one is indirect heat exchanger. Okay, so let's draw it. I will first start with the bottoming cycle here. I will just go from 5, which is here, to 6 in an isentropic manner. Okay, this one is from 5 to 6, and then from 6 to 7. This one will be at 7, and then from the 7 to 8 you will have this 1, that 1, and then from 8 to 1, this point. Let's draw the topping cycle now. For the topping cycle, I will start from 1, and the 1 starts at the 280 kilopascal here. To the point where 1 starts. Okay, and it will go in that direction here. And then it goes to point 2 here. Then from that point you'll just travel point 3 here, and then from that point 3 you will go back to the same pressure as this one here. I will not intersect the ones here, but you have to know that these are the same pressures. This one will be that point 4, and this is the direction that you are traveling, and this one will go in that way. This one is 4, and this one is back to 1. Okay. This is the topping cycle here, and this one is the bottoming cycle. Now, what is the advantage here? Advantage is that you have noticed that I'm using the same pressure differences here, 140 to 720, but with cascade refrigeration system, you can even increase the temperature at this range here, for example, 1800 kilopascal, because you have two cycles here. So instead of, for example, for topping cycle, it can be separate, as I said. This one is 140 here, but you can put this one as, for example, 720. If you put the minimum limit of that one to that pressure, you can see that the TH will increase to 600 degrees, 60 degrees Celsius. Okay. This is the first advantage of the cascade refrigeration system. And another difference, the advantage of this one is that, so first advantage, let me just write it. So TH and the T low, it can be very high and low. But this one can be very high and this can be very, very low, because you can top this one to that place and the bottom one can be in this place. So you can even decrease it. Okay, because these are that independent. So that these are independent. So you can move this one up and move this one down. You can get very low temperatures and you can get very high temperatures. And the second thing here is that it is very similar to intercooling. If you have not done the cascade refrigeration system, what you could do is that you have to go along this line. So you can see that this one is 2 prime. So that without cascade, very similar to intercooling. So that you will have that H2 prime, enthalpy with 2 prime. Therefore, that work in with 2 prime will be greater than work in 2. Okay. This is also the advantage of the cascade refrigeration system, that you have the less work, because you have started from that one to this one and to that one to this one. And see, you don't have any more enthalpy with respect to the without the cascade system. Okay. And one more advantage for the cascade refrigeration system is that, for example, if you have only used the topping cycle, if you have only used this one, what you could do is that you have to go from one to that stage and then to that one, and you have to go back to this part and close the cycle here. Say that this one is that 8 prime. Okay. If you have not used the bottoming cycle here, you have to go from 3 to 8 prime by flow restriction or the thermal expansion valve. But if you have used the cascade, therefore you have more cooling. Okay, so that the third one is that with cascade, so that QL increased. Why it increased? Because by enthalpy at 8 prime minus enthalpy at 8. In this amount of the QL, you have the increased amount of the QL. But if there was no bottoming cycle, this one could be the cycle that you are operating. This one. But with using the topping cycle and the bottoming cycle, we have increased the cooling part with this range here. Okay, so this is another advantage of the cascade refrigeration system. And here I've used the same refrigerant, the different refrigerants can also be used. Okay, so that economized cycle with the flash chamber or the flash intercooler here. Let's see this one. So here I have the compressor one, and then from that compressor one you have this condenser, and then from that condenser I will have the thermal expansion valve, and then from that thermal expansion valve I will have the flash chamber here. This one is flash chamber. Okay, and then the flow into this flash chamber, because the TXV outlet, this one is mixture. Okay, and then you will have a dripping into that system. You will have the drippings here, and the lower part of it here you will have the liquid. That upper part here will have the vapor. Okay, so that in this flash chamber I can separate the two components here, with the one as a liquid and the other one as a vapor. Okay, now let's see the next component here. So I can take the liquid part of this one, the liquid one alone. Okay, and I can use the TXV here, the thermal expansion valve, and then what I can do is that I will just replace the evaporator. From that evaporator I will have the compressor here. Okay, this is the compressor. So this is the liquid part, and I will take the vapor part here. So this one only liquid. This part, just add it. Only liquid here. And then here you have taken only vapor. Okay. So this one goes there. That one goes here. You will have the T mixing chamber. You are mixing the outlet of this compressor with the outlet of the saturated vapor, only vapor. This one is saturated vapor from the flash chamber. Okay, this one is adiabatic. You can see that this one is adiabatic, and you are sending back the compressor one. Okay, so I can put the numbers here. This one is 1, this one is 2, and this one is 3. This one is 4, and then you will have that 5. You have 6. You have 7 and 8. Here you will have the 9, and back to 1 here. Okay, this is the economized cycle with a flash chamber or the flash intercooler. Okay, so the advantage of this one is that, so here you have the intercooling also, but the intercooling here, it is not done by an additional heat exchanger here, but it is done by as T mixing chamber. You can see that the outlet of this compressor here is mixed with this outlet here, and it drops the temperature, and therefore the compressor one inlet is having a lower temperature. Now let's draw the cycle, and you can see the intercooling effect on this cycle, and just let me write the values. And the P6 is same as P7 because it's evaporator, and the P8 is greater than P7, and the P8 is equal to P9, which is heat exchanger. This one is heat exchanger. P8 is same as P9, okay, and P9 is same as P1. P8 and the P4 and the P5, all of them are the same. Because this one is heat exchanger, this one is heat exchanger, and this one, there is mixing here. Therefore, all of them has the same pressure here. And then you will have that P4 is less than P3 here. It is less than P3, and the P3 is same as P2 value, and the P2 is greater than P1. Okay, so I have all of the values here. So let me see. P6 value same as P7, and if I've not compared the 5 and the 6 value here, the P5 should be less than P, should be greater than actually. Let me just write it here. P5 is greater than P6. And if you compare the values here, you can see that there is one pressure line here. Let me just write it. You will have that P max, maximum pressure, that one will be equal to P2. This is the maximum pressure, which is same as P3. You have that medium pressure, which is that P4. Okay, and then this P4 drops one more time to P6. P minimum is P6. You have three isobar lines. Okay, just I will take the same one as in the previous case. I will just take the 140, 280, and 720. Okay, let's do that. For the first compressor, goes from the 7 to 8, and the 7 is the minimum, and the 8 is the medium. This one is the medium, and this one is the minimum. I will have the 7 here, it goes to 8. Okay, and then this 8 is mixed with the 9 here. This one has the higher enthalpy than that one because this is compressor outlet and this is the saturated vapor outlet. So this one is superheated. Okay, but this one is saturated. So therefore, this one has higher enthalpy than that one, but during the mixing process, this one, the enthalpy drops to 1. We'll have the 1 here. So I will start with the, so you should also notice that this compressor outlet here is superheated, and this one is that saturated, but 8 and the 9 is mixed. 8 is greater than enthalpy of 9. Okay, and when mixed, you will have that enthalpy of 1, which will be less than enthalpy of 8 and greater than enthalpy of 9. Let's start here. You will have that 7. From 7 you will go to up to 8 here. But you should notice that I will also take the value as the P minimum. It will be 140, and the P medium 280, and the P maximum it is 720. Okay, so you have gone from 7 to 8. Okay, and then 8 and the 9 is mixed, and 9 is here. You can see it is saturated vapor. This is the 9. These are mixed together, and you will have some point that is in between. So you will have the point here. This one will be 9. If I get it closer. So you can see the 9. It is, sorry, that it is not 9. It is that We go back to here. It is 1. 1 is less than 8, but it is greater than 9. Okay, this is the point 1 here. Okay, let me just write the 1 value here. This one is at point 1. Okay. And then from point 1 to 2, you will have the compressor stage. But you should notice that if I draw it separately here, so this is 0.9, this is 0.8, and here you will have that 1. So this one goes in that direction, that one goes in this direction. Okay? The enthalpy of this one drops to 1, and the enthalpy of 9 increases to 1. And then, let me complete it. And then from 2 to 3, you will have the condenser stage. In the 3 to 4, you have the thermal expansion valve. Then this thermal expansion valve is separated into 2 parts. One is that 5, which is only liquid, and one is that 9. 9 is here, so I've just shown it. This is 9, and then I will have to show also the, which is 5. Sorry, I have the arrow in that opposite direction here. This is 5, and then you will have this as 9. Okay, and then from 5 to 6, you will have the thermal expansion valve again. I will just draw the 5 here, and then 6, you will have the thermal expansion valve again. And from the 6 to 7, you will have this. Okay, now you can see the advantage here. Again, you have the intercooling effect here. That's intercooling effect. Let me just draw it closer. You can see the intercooling effect here. If you have not used the intercooling, you have to compress it from 7 to 2 prime here. You have to go in that direction. But due to intercooling effect, you have decreased the outlet of the compressor 1 to some medium pressure of 1 here, then compressed it again. So they have the drop in the compressor work. As well as you have the QL effect here, because if you have not used the part here, then you have to drop the pressure from 3 to 6 prime here. You can see that part, and therefore you will have the drop in this QL, lower pressure, lower, that evaporator part. But since you are using 2 compressors, you have the additional heat cooling effect due to this area here. So let me just write it here. So the first is that intercooling effect. That intercooling effect allows that H8 drops to H1. Okay, this is the first advantage, and the second advantage is that if you have not used this cascade system, what you will have is that you have to compress, you have to expand it from 3 to 6 prime. Okay. So QL advantage, you will have that QL advantage, which is equal to that H6 prime minus H6. Good. That's it. This is the intercooler. So notice it. Intercooler. So the one more, let's see, the refrigeration cycle is that flash intercooled cycle with a flash chamber or flash tank. It is very similar to that one. Instead of you don't have here the T mixing chamber. So for this one, you don't have the T mixing chamber. Let's see that cycle again. So you will have this compressor 1 here. So you will have that inlet, which is 1, outlet 2. That one goes to condenser. Condenser will have that 3. You will have that thermal expansion valve. This one is 3 again here. You have that thermal expansion valve, and that one goes to 4. Again, you have this flash chamber here. This flash chamber, you will have the drops. And here you will have the liquid state, and then you have the vapor state. Okay, what you are doing is that here you are separating the liquid and the vapor. So here you will have only liquid. X is 0 and X is 1. And then it goes to thermal expansion valve, then goes evaporator, and then goes at the compressor here. Okay, this compressor outlet doesn't go in directly the mixing tank here. What to do is that this outlet, you can send it back to this part here. Okay, then you will have this connected that one. Okay, if I just number it, so you'll have 1 here, 2 here, 3, 4, and this outlet is same as this one here. Then you will have this 5, you'll have 6, then 7, and then 8. Okay. So if I write the pressure values, P2 is greater than P1, P2 is same as P3, and the P4 is less than P3, and the P4 is same as P1, and it is same as P8, and it is same as P5. You can see that these are all the same, and the P6 is less than P5, but P6 is same as P7, and the P8 is greater than P7. Let's see how many pressure lines do I have. So one pressure line is there, one pressure line is there, and one pressure line is there. You have the 3 pressure lines. Okay, so that P max, which is P2, P medium, which is P1, and then you have this P minimum, which is P7. Okay. Now let's draw it, and as you can see, it is also that intercooled cycle here, but instead of using the mixing chamber here, we are using this flash chamber itself as an intercooling effect. Let's see what is the advantage of this one with respect to that one. Okay, so I will just use the same pressure lines here, which will be at 140, again 280, and 720. These are lines that I'm going to use. And if I compare the enthalpy values here, H8, 5, and you have that H1 and H4. Okay, so that H8, it is superheated. Okay. And then you will have this one, mix it with H4, which is mixture. Okay, and this H4 and H1 is that saturated vapor, and H5 is that saturated liquid. And for these ones here, that H8 is maximum. This one has the maximum enthalpy, and the one has the medium enthalpy here. Okay. So let's draw it, and shown on the TS diagram here. I will just start from the 0.7. That 0.7 is compressing to 0.8. Okay, was that direction, and the 8 is mixed with the 4, and then you will have the 2 stages here, and you will have the 5. Let me just add 5 here. 5, and then you will also have the 1 here, and the enthalpy of 8, it drops, and then you will have the 1, and the 1 will be the inlet for this compressor 1 here. So the compressor will compress it from 1 to 2. Okay. Then from 2 to 3 you will have the condenser stage. Okay. From the 3 to 4 you will have the thermal expansion valve. This thermal expansion valve, you will have 2 components here. One is going to that 5 here, and one is going to the 1 here. Okay. Just try it one more time. Goes to 1 here, and then from 5 to 6 you have the intercooling effect again. Sorry, that thermal expansion valve again. Then from the 6 to 7. You can see it is the similar one with the mixing chamber, but here you have more intercooling. You have the intercooling which goes from 8 to 1. And if I zoom it here, you can see that it goes from 8 to 1, but in the previous case it was just moving in the medium range here. So if I zoom that part, you have 8 here, you have the 1 here. Okay, that one drops to 1. And then similarly you have this cooling effect, additional cooling effect. As I said, for this one you have more intercooling. For the previous one you have the less intercooling, but here you have the 8 to 1, but in the previous case it was just from 8 to 1, which is between 9 and 8. Now comes the gas refrigeration cycle, and it is also two different types, and one is that simple one and the other one is that bootstrap one. It is used for the aircrafts and where you are trying to cool the cabin of the aircraft. So the cabin of aircraft, okay, it is that hot. Why it is hot? In reality, that aircraft flies at 11 kilometers altitude, and at this altitude pressure is about 0.3 bars and the temperature is negative 50 degrees Celsius. And at this temperature and at these pressure values, but the cabin of the aircraft is hot. It is due to that is radiation from the sun. There is sun radiation. The second is that you have the equipment, for example, the light and the TV set, etc. inside there. That is the aircraft, and the plus the human body heat loss. Okay. And the third thing here is that the aircraft travels with a speed of 900 kph, and this speed creates friction, and that friction creates the heat. Due to these additional effects of the heat, the cabin of aircraft is hot. And what you are trying to do is that you are trying to cool the cabin, and with the gas refrigeration cycle. It is very similar to Brayton cycle, and now let me show you how it works. Say that this is the engine of aircraft. For engine of this aircraft, we have the air inlet. Okay, this air inlet, you have the ram effect. So what is ramming action here? Let me just note it somewhere here. So that ramming action means that, okay, the velocity is dropped to 0. Okay. In other words, what it means is that enthalpy at state 2 is equal to enthalpy at state 1 plus the velocity at state 1 squared by 2. And because the velocity of the aircraft here, air that enters the aircraft engine is dropped to 0. And this is called the ramming action, that this enthalpy at state is called stagnation enthalpy. So anyway, you have the state 1 here, and then you have the ramming action, which is state 2 here. This ramming action is happening in an isentropic manner, reversible and adiabatic. And then it goes to compressor of aircraft. Okay. And then from that compressor, which is free, you will have the combustion chamber. And then from that one, you will have the turbine, etc. These are the components of the aircraft. These are the components of the aircraft, and the cooling starts from that place, which is state 3. So they take the air line or the pipe from state 3. Okay, this is the outlet of the compressor, and this one firstly goes from an heat exchanger here. You have that heat exchanger. This is the air. Inside this one is only air. Okay, you have the air here, and after that heat exchanger, it moves from a turbine. Okay, here you have the turbine. Okay, so this turbine outlet, this one is sent to cabin. It is at lower temperature, and this lower temperature T low is sent to cabin, and it cools the cabin. Okay, this one's for the passenger cabin. And you can see this is turbine, and this turbine generates some power. Okay, so this power of the turbine So it is the shaft here. So this one is the shaft. That shaft is connected to the turbine with a fan. So here you are using some fan. That fan, it needs electricity. That electricity is provided by this turbine here. This is additional to the engine turbine. What happens is that this fan takes the ram here, ram air. So we have one more line. That the ram air is taken to the fan and then comes to this heat exchanger and it leaves to atmosphere. So what we are trying to do is that, so for the heat exchanger here, so this one is hot. This is the compressor outlet, and this part is hot. Okay, and in heat exchanger it gets cold. Its temperature drops. How the temperature can drop? If we need some fluid that it is at a lower temperature. So this one is at cold temperature here, and here it is hot. That cold temperature fluid is supplied from the ram air, that is by using the fan, and that fan uses its power from the turbine here. Okay, so this is how the aircraft engine works. So let me just draw it on the TS diagram here. So say that this one is the inlet air, and that inlet air is at 35 kilopascal. So that I will have that P1, which is 35 kilopascal. Okay. This P1 after ramming action, so let's say that P2, I don't know the P2 value, say that it is at 50 kilopascal. Okay, then it goes that P3, it can be that 200 kilopascal. Okay, then P3 goes through the heat exchanger here, then I will have that 4 value here. P4 is same as P3, this is heat exchanger, then it goes from the turbine, which is 5. But P5 should be the same as the pressure of the cabin. Okay, the air that leaves the turbine, it should be the same pressure at the cabin, otherwise it will create a discomfort. Now let's start. So that P1 is at 35 kilopascal, and it is, so this is the T1, and the T1 is at negative 50 degrees Celsius. And then we just start it. You have negative 50 here. So that here I start the ramming to A. So I don't know the ramming where it ends, but I assume that it is 50 kilopascal, but I should go to 200 kilopascal. Let me just go to 200 kilopascal, a value here. Okay, this is 0.3, and in between I will have that 0.2. Okay, this one is the ramming action, this one is the one, this is the direction that I will travel, and the ramming is isentropic. Okay, and also the compressor work is isentropic. Okay, and then from 3 to it's the next stage is that 3 to 4. You have the heat exchanger here where the temperature drops and to a value of the P4. I don't know that. So P4 and the P3 is the same here. Okay, P3 and the P4 is the same. This one is 4 value in that direction. Okay, this is the exchanger, and then from P4 to P5 you will have the drop in pressure, and it is a isentropic device again, and it is a turbine. Let me just do that. Okay, you can see that 5 is at 100 kilopascal P cabin, and I'm assuming that this one is 100 kilopascal. Okay. Okay. And as you can notice from here is that 5 temperature, you can see it is negative 40 degrees Celsius. So it means that it can cool the cabin. So that this one from that P5 to that is the cabin temperature is that, let me say that T cabin is, for example, that 25 degrees Celsius. For example, this one. So it means that so the turbine outlet 5, it will be used for the cooling process, and the cooling will happen at constant pressure, and this one will be at 6. So it's 0.6. Okay, and the 5 to 6 is cooling. Okay, so that T5 is negative 40 and the T6 is 30 degrees Celsius. The temperature of the outlet of the turbine increases from 5 to 6. This is for the gas, but this one is not the bootstrap. This one is simple. So sorry for that one. So I've just used the bootstrap here. Okay, but this one is simple. Okay, this one is simple. Now comes the second one, which is the bootstrap, will be this one. This one will be that bootstrap method. So this is more advanced one than the gas refrigeration cycle, which is the simple one. This will be more advanced. Let's see how it happens now. Similarly, as the previous one, you will have that engine here. Okay, for that engine, you will have this is the inlet, which is 1. Then you will have that ramming action. You will have that 2 here. Then you will have that compressor, outlet of that compressor, and you will have this. You will have the combustion in 4, and then you will have the turbine. So I will not write the 4 value here. This is the 3. Okay, now let's start it, and then from that 3 value here, this is the compressor. So let me just start here. I will have the first heat exchanger, again, and then I'm using a second compressor here. So compressor 2. Then this heat exchanger called is air cooler. These are having names, and this is called the secondary compressor. This one is called main compressor. Sorry, that's not compressor, that's combustion. Okay, and this one is that main compressor. These are just names, it's not so important. And you can see the similarity here. So in the previous case, it was that compressor, heat exchanger, and the turbine. Now, instead of fan, I have the compressor 2 instead of the fan here. So you can see the similarity. I have the fan here, but I have the compressor 2 here. Then from that compressor 2, I will have one more heat exchanger. So heat exchanger again, and this is called aftercooler. Okay, then it goes in that direction here, and then the turbine, and then it goes to cabin. Okay, and here I have that is 2 heat exchangers, and here it is hot, then it drops to colder value, then it is again cold, and then it drops to hot, then from that one it becomes cold again. So it means that at this stage from hot to cold, I need the fluid that is cold and it becomes hot. That one is again supplied by this ram air here again. Okay, and this one is for the exit to atmosphere. Okay, this is at entrance it is cold, and at outlet it is hot. And I will supply one more ram air here. I will take one more ram air from that line, and it will go to next exchanger. Again, it is exit the atmosphere. Okay, and this one at entrance it is cold, and then it becomes hot. At the same time, this one becomes hot, and this one becomes cold. And here the compressor 2, secondary compressor, and this one is driven by turbine. You can see the turbine here. They have the same shaft that is connected to compressor 2. This one drives that one. Okay, so if I just put numbers here, let's put some numbers. So I have the 2 value here, I have the 3 value here of air cooler, and then I will have that just using the different color. You may find you will have that 4, and then you will have that 5, then you will have that 6, and then you will have that 7. Okay, similarly to the previous one, I will have that 1 here. So that P1 will be 0.35 bars, and then T1 is negative 50 degrees Celsius. Let's just use it. I will start from that part. Okay, this one is 0.1. 0.1 increases the by ramming action to 2, and from that 2 it increases the value of 3. And I will just use that. P3 is 200 kilopascal. Okay. And then from 2 to 3 you have the first compressor, and then the pressure drops. So the temperature drops actually. This one is 0.2, 3, and this one is 0.2. This is the direction it moves. And then I will have that drop in temperature to 4. I don't know how much the temperature will drop. This actually depends on the application. 4 here. So you can see that this is very similar to intercooling. They are cooling the compressor between these two stages. So you will have that 4 here. Then from the 4 to back to, you will have the 5. Okay, so you have this 1 to 2, which is RAM, and the 2 to 3 is compressor 1, and the 4 to, we just use as 5, it is compressor 2. I don't know what is the pressure ratio of the compressor 2. Let's assume that this one is here. So this is 0.5, and let me just write it. 1 to 2 is RAM, 2, 3 is compressor 1, 3 to 4 it is air cooler, 4 to 5 it is compressor 2, and then you will have this, which is as the, that is 5 to 6 will be that after cooler here. So I don't know the values here. This one will be that 5 to 6 after cooler, and then from that 6 to 7 it will be turbine. The turbine value to drop it, the cabin pressure. This is the turbine, and 6 to 7 is turbine, and it drops the pressure to cabin. So P7 is P cabin, and it is 100 kilopascal. Okay, and then you will have this cooling effect that goes along this line here. This one is 7. The values can be wrong, but then it is in view how the shape is affected. So this part is the cooling part. It should go to 25 degrees Celsius, not the 25 degrees Celsius. Okay, this is the cooling part, and this is the end of the cooling, which is the cabin temperature. Okay, this is how it looks like for the bootstrap method. And here you can see that you have the compressor too, which is driven by the turbine. For the bootstrap method cooling system, you cannot use can't use for ground cooling. What it means is that you can see that the ram air, it travels through these heat exchangers here by itself. Okay. For this one, the ram air is used by a fan that drives itself to the turbine here for the heat exchanger. For this one, the velocity of the aircraft, that is the required thing that drives the ram air around these heat exchangers. Therefore, if the aircraft is on the ground, so there is no velocity and for inlet, and therefore these heat exchangers cannot work, and therefore this bootstrap cooling system only works when the aircraft is cruising in the air. Okay, now last thing is for the absorption refrigeration system. For the absorption refrigeration system, we are using two different fluids, and one will be the gas and the other one will be, for example, liquid, or it can be that liquid and the salt, or liquid can be salt. So what we are doing is that it is based on the absorption process. Okay, so the absorption process, the famous one is that, for example, you have the cola. Here you have the gas as well as the liquid. Okay, so that at cold temperature, at cold T, absorption is high. So that it means that therefore it is recommended to drink the cola at cold temperature, because the gas is dissolved in liquid in higher amount than in the higher temperature. Okay, therefore at cold temperature you have the absorption, at high temperature you have the desorption, opposite of absorption. So what it means is that at low temperature the gas and the liquid is in the same phase as in the cola. As you increase the temperature, gas and liquid separates, and you will have two different distinct phases that is dominating inside the cola. Okay, now let's see how the absorption refrigeration system works. And the first thing here is that you have the same processes as in the vapor compression cycle. Here you have the TXV, and here you will have that condenser. Here you will have this evaporator. Okay, this is how it works, and that one goes there, this one goes here, and there, and here. So here, this I will put just numbers here, but for the part that is dominating here, you are not using a compressor, but you are using a different system. Let me just show it to you. You will have this generator here. Okay, so in this generator you will have two fluids. For example, in one side you will have the water. So here you will have water, and on the other side you will have this, for example, salt. This salt, it travels in that direction to a absorption part. Okay, you can see that here water travels and it goes back to this state here, and the water and the salt, they are absorbed in this absorption unit. So what we are doing is that you need some cold water. So here you are supplying some cold fluid, and that cold fluid leaves as hot. Yes, it is very similar to cola. So you need a low temperature here, and during this absorption process, it's exothermic process, and you will have that Q out. Okay, and then, so water and the salt. This one is salt and this one is water. They are mixed together, and it is sent back to this generator here. So how do we send it back to this generator here? We are using some pump. Okay, this pump sends the mixture back to this place here. It is now mixture. Okay, and as you can notice that the absorption unit has lower pressure than the generator part, because here in between you are using that pump. So therefore what we are needing is that this salt part here, I will have some valve. That valve drops the pressure of the salt to the same pressure as the absorption unit. Okay, because you can also notice that here you have the condenser, which is same pressure as the generator, but here you have the TXV, which where the pressure drops. Okay, after evaporator, heat exchanger. These are heat exchangers, they have the same pressure. Okay, and here you can add one more heat exchanger. For example, at some place here, you can add one more heat exchanger. Since this one is hot, that one is cold, we can give heat from this part to that one. Okay, this line is hot and that line is cold. Okay. Okay, so this one is heat exchanger. This is how the absorption system works, and for the absorption unit you need some cold fluid, but for the generator one, this part, you need some energy. And that energy can be, for example, solar energy. Okay, solar energy that falls on this generator, it will heat it, and the two fluids will separate, and one part you will have the water, and on the other part you will have the salt. So what are the advantages? Let me just write it. First advantage is that you are using pump. Okay, and the work of pump is much smaller than work of compressor. And the second one is that you are using the solar energy. Okay, this is the second advantage of this cycle here. And then what else do I can? What else can I write here? And this is the advantage of the cycle, and disadvantage is that the first one is that COP is very low. It's about 0.3. But for the COP of the refrigeration systems, it is about 3 to 4. You can see it is very high, but for this one it is very low. The second thing is that this one is very bulky and a complex system. Why it is very bulky and a complex system? It is due to heat exchangers. Okay, heat exchanger, which is here you have the absorption and as well as the generator. The problem for the absorption is that for this absorption process, you need a larger surface area. Larger surface area means that larger unit, and therefore this one is a bulky and a complex unit. This one provides the QL. Okay, this is the absorption refrigeration system, and in some places, in some industries, they are using it due to cheap cost, because here you have the solar energy. With this one, I have finished the refrigeration cycles, and good luck to you.